So, welcome to section 6. There are many problems, so we'll see if I'll be able to finish them within this year or within December. So, well, let's get the show on the road. Now, we are operating in the Gaussian integers and needs to show that d3 vanishes and d4 is real and positive. So, the definition I've written them. I have the book in front of me. 60 times d4 and d3 equals 140 d6. And the Gaussian integers presume they are well known. So what I was thinking here was that every Gaussian integer z has 3 cousins, and all of them to the fourth give the same. But I don't think that's relevant, really. Now d2 vanishes. Oh, then we can put those to the second. So we see this family gives together naught. That's the sum of the squares. We were actually going to compute the sum of the fourth powers. That was, of course, why I should think that the fourth power is. Oh, I read the wrong problem. I was reading problem B. So d3 vanishes. So when we go to set to the third, then this is minus I set to this. We are going to sixth power. So that's minus set to the sixth, set to the sixth, minus set to the sixth. So the sum vanishes. Right. So that implies that d3 vanishes. d2 is real. Then one thing is z, the other is z bar. So coupling the numbers with their conjugates and adding those give a real number. So that's it's very simple that G2 is real. So the principle here is pairing conjugates. That doesn't hold for the reals, but they will give a real sum, whatever. Now, the only missing point is that it's non-zero. I think it has to be non-zero for the expansion to make sense. I don't think we're supposed to use that. G8, 10, etc. are given algebraically by G4 and G6, so that if they both vanish, then the whole series 6, 2 will vanish, so that the Weierstrass P function simply becomes 1 divided by Z square, and that's not a double periodic function. I don't think that's what they meant we should think. Another way is to use the moduli of the addends in this sum. I don't like to do that. I could try to work it out by myself, but doing it here, it's an idea that maybe we could see that the unity and the family around unity will give 4 when added, and maybe the rest can't give as much. Or maybe some other idea like that, but I'll leave that for the moment. So we finish A here. So we go to B. We have omega to the third is unity. And that means that when we look at Z, omega Z, and omega squared Z, and then put them to the, now what, it's G2 vanishes, so put them to the 4th power. Then this becomes omega Z to the 4th. And now so the sum but this vanishes. That's the minimal polynomial for, I've forgotten what we call this, the third root. So that implies G2 vanishes. Then we have to show that G3 is real. Now, what did we do up here? That was comparing conjugates. So z to the sixth and z to the sixth is real. Or rather, it's 1 divided by them. So that's a reordering, but it's absolutely convergent anyway, so that's obvious. Now the problem that it's non-zero. Oh, it may be negative and positive as it might be. Yeah. I have no idea except what I already said. C, we multiply the lattice, the generators of the lattice with C. This is trivial. It's just applying the definition. And then prove that it is of this form for some lattice L. Yes. So if we take this guy, for instance, with G3 vanishing, then we can use the Gaussian integers as a model. So and if we use CL instead, it is C to the minus sixth, no, to the minus fourth. And since this is distinct from 0, and this is distinct from 0, if they were both 0, then of course we wouldn't have an elliptic curve. So this is assumed to be distinct from 0 then. So C to the fourth equals G2 of L divided by G2 of CL. So it's just finding a solution to this. There are 4 to choose from. and then we have lattices giving that curve. And in case G2 vanishes and G3 not, then it's exactly the same. We get C to the sixth and the other, so it's analogous. So we have one problem remaining. I'd like to have a very principled way of doing it. My argument with the sums I think is very good, but I should think that there was a better way of doing it. Going back to basics somehow, but I don't see that at the moment, so we'll just finish here.